let's go ahead and solve this problem. This is a force problem, so we know we're going to have to use Newton's laws. So let's go ahead and do that for the x-axis. So along the x-axis, we don't see any forces. So that implies that there is no acceleration, so the velocity along the x-axis is going to be constant. Now along the y-axis, I see exactly one force, and it points down. So I'm going to write minus mg, and that's going to be equal to ma, the acceleration. And so notice the m's cancel, and I get that the acceleration is minus g, which is the statement that everything falls with the same acceleration according to gravity, right, if subject to gravity. So bottom line is that the ball is just falling down with constant acceleration. So since it's constant acceleration, the motion is going to be described by the kinematic equation. So I'm just going to go ahead and write down the kinematic equations so that I can plug in later. So here are my kinematic equations, and these equations, oops, not V here, this is going to be A. These equations are going to be true for each axis. So along the x-axis, well, the velocity is constant, so this actually becomes fairly simple. So let's look at this. Along the x-axis, the final position is going to be d. The initial position is x equals 0. And the velocity is constant. Now, what is the velocity along the x-axis? Here's my initial velocity. So I can go ahead and decompose that. Let me do this in red so it's a little bit easier to see. Right? I can decompose that velocity into its x component and its y component here. And so the x component is going to be v naught times cosine theta because it's adjacent to the angle. So let's go ahead and plug all of this stuff in. The final position is x equal to d. The initial position is 0. The initial velocity along the x-axis is v naught cos theta times df. And this term over here is going to be 0 because the acceleration along the x-axis is 0. Okay, this is the first relation. Along the y-axis, what do I have? Let's see, the ball starts here, which is y equals 0, and it ends here, which is y equals 0. So I'm going to have 0 is the final position, is equal to 0, which is the initial velocity, plus this term over here, so I need the initial velocity along the y-axis. That's going to be this component. That's going to be v0 sine theta because it's opposite of the angle. So v0 sine theta times df. And then for this term here, the acceleration is minus g. So I'm going to have minus 1/2 g times tf squared. And so notice in this equation over here, I can divide by tf on both sides. And so that means that this will cancel a factor of tf on the right. And I am going to end up with 0 is equal to v naught sine theta minus 1/2 g tf. And this is the second relation. I could also go ahead and plug into the equation for the velocity along the y-axis, but since I didn't get asked about the velocity along the y-axis, I'm not going to bother to write that equation. Okay, so these are the relations that we have derived, and so from this point on, it's algebra. So see if you can do the algebra on your own to figure out how far the ball is going to go.